Ms. Beverly Chitu, who is a current MPhil, hopefully soon doctoral student, in what is her second seminar. And in her particular case, these seminars are to show the progression in her research towards her upgrading from her current status of MPhil to the doctorate. And Beverly's presentation, as you will see shortly, is excellent. There's a lot to be learned, so I'm glad it's being taped, because those who have missed it will be able to go over it very slowly and be able to learn a few things. Those of you who are here will have the privilege of seeing, as I said, a very well-prepared presentation on a particular phenomenon, the phenomenon of adsorption. Okay, and this is something that could be both in gases and in liquids. In her case, it's in liquids. But the general science behind it is important, and we have more than one student at UTT who is investigating these phenomena, because it's more than one relationship. And I have to say that I'm very happy, and my compliments to Dr. Clint Sutherland, who is Beverly's supervisor, on the preparation of this student. I mean, and my compliments to Beverly as well for her work ethic and her, you know, her whole attitude towards learning and progressing and researching. So those of you who will watch this tape afterwards have that to learn. You know, what you will see didn't just come from pulling it out like that. You could tell that it came from hard work, along with talent, of course, but hard work is there. So let me get on to it and let Beverly present. All right, as I said, this is the second series, and I believe second one in the series of her topic, her presentations on her work, and the first one is there. So those of you who might find this a little bit hard, and I mean, it is a little bit complex, although clear, we'll be able to look at the first presentation, get some background from that, and then follow on this one. So Beverly, without further ado, I don't know if you have a mic on you? Or?
No, I'm using this. Okay. Good afternoon, everyone. Thank you, Professor Stout, for the introduction, and thank you all for attending today's session. My research focuses on investigating and optimizing the reuse potential of lime iron sludge. It has specific emphasis on the reuse of the sludge for modification of weak soils and for the removal and recovery of phosphorus from wastewater. This afternoon's presentation focuses on the second part of the research, which is the investigation and optimization of phosphate adsorption using water treatment plant sludge. I will start by speaking about the importance of phosphorus removal from wastewater and the research objectives, after which I will describe the methodology and some of the major findings of the study. I will then go on to speak briefly about the future work and some of the benefits of the study. So why remove phosphorus from wastewater? What is the importance of phosphorus? Phosphorus is an essential constituent of all living matter, and it is a crucial element of numerous industrial and agricultural processes. It is critical that phosphorus is a non-renewable resource, and global reserves are estimated to be depleted or near totally depleted by the year 2050, which is only 36 years from now. At the same time, significant amounts of phosphorus are consumed via various daily life activities, thus making phosphorus one of the main contaminants of wastewater. Excessive concentrations of this limiting reactant can stimulate eutrophication in lakes and streams, which deteriorates the quality of the water and consequently increases the cost of water treatment. Physical chemical processes such as ion exchange, dissolved air flotation, membrane filtration, high-rate sedimentation, coagulation, and adsorption are used extensively for phosphorus removal. And amongst these, adsorption is one of the most common techniques in current use. However, the acquisition of adsorbents, which are both easily available and efficient, remains a significant challenge to small-scale wastewater application. Several researchers have reported that water treatment sludge exhibits potential for phosphorus adsorption. However, these studies have focused predominantly on alum sludge, and there is minimal information available on the phosphate adsorption potential of other types of water treatment sludge. Hence, this study aims to investigate and optimize the use of water treatment sludge for the adsorption of phosphorus from wastewater. And 3 types of sludges will be studied. These are lime iron sludge, lime sludge, and alum sludge. And the photographs that you see here were taken after the samples were prepared for experimentation. So once it was collected from the treatment facility, it was dried in a convection oven at 105 degrees, after which it was pulverized and then sieved to pass 2.36 millimeters. The study was conducted in batch mode. Kinetic experiments were conducted to determine the rate at which the adsorption process proceeds, as well as the time taken to reach equilibrium. The adsorption process was optimized by varying the agitation, pH, and desorption studies were also conducted. Following this, equilibrium studies were conducted to determine the maximum adsorption capacities of the different materials, and the adsorption parameters were optimized by varying the adsorbate concentration, the adsorbent concentration, and the temperature. And in this study, the adsorbate refers to the phosphate concentration, and the adsorbent refers to the water treatment sludge that was used. These are some of the equipment that were used in the research. A mechanical agitator, which was used to vary the agitation as well as the reaction time. A scanning electron microscope, and this was used to assess the morphological structure of the water treatment sludge. This was done at various phases in the research. A UV spectrophotometer, which was used to determine the phosphate concentration using the molybdate ascorbic acid method with single reagent. An atomic adsorption spectrophotometer, which was used to determine the elemental composition of the sludge, and again, this was done at different phases in the research. A Buckner funnel and vacuum system was used to separate reaction mixtures, and a Hack multimeter was used for measurement of conductivity and pH. For the findings of the study now, I will start by talking about the composition of the sludge before adsorption studies. And as I mentioned previously, this was done using atomic adsorption spectrophotometry. The results presented in Table 1 illustrate that aluminum was a dominant component present in alum sludge, while calcium was a dominant component present in lime sludge. For lime iron sludge, both calcium and iron dominated, and according to several authors, aluminum and iron are the dominant phosphate adsorption components present in water treatment sludge, and calcium can aid in phosphate removal via precipitation. So what is adsorption? Adsorption is essentially the adhesion of atoms, ions, or molecules onto a surface. There are several mechanisms by which this may take place. For example, physical adsorption due to non-specific forces of attraction, electrostatic adsorption due to Coulombic forces of attraction, or specific adsorption due to chemical forces of attraction. For this study, the adsorption data was modeled in order to gain insight into the mechanism of phosphate adsorption onto water treatment sludge, to quantify the effect of varying the adsorbate and adsorbent parameters, and to aid in the eventual development of predictive models that can enable process design of batch treatment systems. Data obtained from kinetic studies were fitted to 4 popular kinetic models, and each of this was developed on a different premise. This was used to assess the rate at which the adsorption reaction proceeds and to elucidate the mechanism of adsorption. The first model used was a pseudo-first-order model, and this was developed by Lagergren. And this model is based on the assumption that physical processes are rate-limiting. And over here, you have the nonlinear form of the model and the linear form. The pseudo-second-order model was developed by Ho and McKay, and this model assumes that chemisorption is the operative reaction mechanism and is rate-limiting, and again, the nonlinear followed by the linear forms of the model. The intraparticle diffusion model is based on the assumption that intraparticle diffusion controls the adsorption process, and this was developed by Weber and Morris. And finally, the diffusion chemisorption model, which is an empirical model developed by Sutherland and Venkobacha to describe the adsorption onto heterogeneous surfaces. This model assumes that both diffusion and chemisorption controls the adsorption process. And here you have the nonlinear form, which can be linearized into this equation. After the data was fitted to the various kinetic models, the goodness of fit was assessed using the coefficients of determination and the following nonlinear error functions. So you have the relative percent error, Marquardt percent standard deviation, and the hybrid error functions. Table 2 presents the results from linear and nonlinear regression analysis of the kinetic models. For linear regression analysis, the data was first fitted to the linear forms of the kinetic models. The coefficients of determinations and the model parameters were determined. These parameters were used to generate theoretical curves that were compared to the primary experimental curves by calculating the error functions. For nonlinear regression, the data was fitted to the nonlinear forms of the model. Again, the model parameters were determined in this case using the Levenberg algorithm. And these model parameters were used to generate theoretical curves that were compared to the experimental curves by calculating the error functions. A pass-fail method was used to select the most appropriate kinetic model based on these results. And this pass-fail method had three categories. Firstly, the coefficients of determination was assessed. Values closer to 1 indicates good conformity of the model. And for the three sludges studied, the pseudo-second order and the diffusion chemisorption model showed good conformity to the model, while the pseudo-first order and the intraparticle diffusion model showed lower conformity. The second category was to assess the error functions. The magnitude of the error functions was assessed, where the smaller the error values, the better the fit of the model. And again, the results indicated that the pseudo-first order and intraparticle diffusion model produced considerably high error values, while the pseudo-second order and the diffusion chemisorption model produced relatively small errors. And the third category was to look at the similarity between the errors generated from linear regression and nonlinear regression. For the three sludges that were studied, it was found that the pseudo-first order, pseudo-second order, and intraparticle diffusion model produced errors in linear regression that was considerably different from those generated using nonlinear regression. Whereas the diffusion chemisorption model was able to produce error values in linear regression which were similar to those generated using nonlinear regression. The graph here shows the fit of the diffusion chemisorption model for the experimental data for the different sludges that were studied. And this model was selected as the most appropriate and used for further investigation of adsorption parameters. The effect of agitation was studied within the range of 150 to 350 RPMs. Table 3 here shows the results for lime iron sludge. From here, you can see that with increasing agitation, both the overall rate and the initial rate of adsorption increased. This may be due to an increase in the rate of diffusion resulting from enhancement of turbulence, which tends to decrease the thickness of the liquid boundary layer surrounding the adsorbent particles. This increase in adsorption with increasing agitation confirms that film diffusion is involved in the adsorption process. It was noted, however, that the increase in both the overall rate of adsorption and the initial rate of adsorption was marginal as the agitation increased from 250 to 350, whereas there was a considerable increase for a change in agitation from 150 to 250 RPMs. This may be due to an increased desorption tendency resulting from vigorous mixing, which tends to displace some of the adsorbate molecules from the adsorption site. Taking this marginal increase into consideration, together with the fact that an increase in agitation from 250 to 350 necessitates a higher energy input and thus an increased cost, 250 RPMs was selected as the optimum agitation. Now, I said that these results are for lime iron sludge. Similar trends were obtained for lime sludge and alum sludge. Table 4 here shows the initial and overall rates of adsorption for the different sludges that were studied at the optimum agitation, 250 RPMs. And from here, you can see that the lime iron sludge produced the highest initial and overall rate of adsorption, illustrating its significance as a potential phosphate adsorbent. The effect of pH was studied within the range 2 and 10, and the results indicated that alum sludge favored slightly acidic conditions, pH 4, while lime sludge and lime iron sludge favored slightly basic conditions, pH 8. Now, depending on the solution pH, phosphate can exist in different forms. At pH less than 3, it is weakly attached, whereas pH between 4 and 10, it is readily adsorbed. pH beyond 10, it tends to compete with OH ions for adsorption sites on the adsorbent. Table 5 here shows the diffusion chemisorption parameters for the different sludges at their optimum pH. From here, you can see that although alum sludge produced the highest initial and overall rate of adsorption, it reported the lowest adsorption capacity, while lime iron sludge produced the highest adsorption capacity, again illustrating its potential as a phosphate adsorbent. Figure 3 here shows the adsorption capacities of the different sludges for a constant phosphate concentration of 10.5 milligrams per liter, which is typical of municipal wastewater, at the optimum agitation, 250 RPMs, and each of the sludge was used at their optimum pH. From here, you can see that the adsorption capacities of the lime iron sludge was significantly higher. It was approximately 2.3 milligrams per liter. And this was approximately 34% and 52% higher than that for lime sludge and alum sludge, respectively. Additionally, the time taken to reach equilibrium was approximately 6 hours for the 3 sludges that were studied. Recall that I mentioned earlier that equilibrium studies were conducted where the adsorbent concentration, the adsorbate concentration, and temperature was varied in order to further elucidate the mechanism of adsorption and to determine the maximum adsorption capacities of the different materials. Equilibrium studies were conducted where the adsorbent concentration, the adsorbate concentration, and the temperature was varied. In order to further elucidate the mechanism of adsorption, the data obtained from these equilibrium studies were fitted to various 2 and 3 parameter isotherms. And the first isotherm used was the Freundlich isotherm. This is an empirical 2-parameter model used to describe adsorption onto heterogeneous surfaces as well as multi-layer adsorption. Over here, you have the nonlinear form of the model, followed by the linear form of the model. The Langmuir isotherm is a 2-parameter model used to describe adsorption onto homogeneous surfaces. This model assumes that adsorption sites exhibit equal affinity for adsorbate molecules and are capable of adsorbing one molecule, thus forming a monolayer. This is the nonlinear form of the Langmuir isotherm, and it can be linearized into 4 equations, all of which are used in this investigation. The Redlich-Peterson is a hybrid 3-parameter isotherm which incorporates features of both the Langmuir and the Freundlich isotherm. And the SIPS is a combined form of the Langmuir and the Freundlich isotherm, and this is used to describe adsorption onto heterogeneous surfaces. The 2-parameter models was assessed using both linear and nonlinear regression analysis. The results from linear regression analysis here shows that the Langmuir isotherm was generally able to produce a more accurate fit of the data than the Freundlich isotherm. And a comparison of the linear and nonlinear regression analysis indicated that in this instance, linear regression was able to produce a slightly more accurate fit of the data. The 3-parameter models were assessed using nonlinear regression analysis, and the results presented here shows that the SIPS isotherm provided a more accurate fit for the lime sludge and the lime iron sludge, while the Redlich-Peterson provided a better fit for the alum sludge. Overall, the alum sludge was best represented by the 3-parameter Redlich isotherm, while both the lime sludge and the lime iron sludge was best represented by the 2-parameter Langmuir isotherm. The graph here shows the best fitting isotherms for the experimental data obtained for the different sludges. So for lime iron sludge, it was best represented by the Langmuir type 1 isotherm. For the lime sludge, it was best represented by the Langmuir type 4. And for the alum sludge, it was best represented by the Redlich-Peterson isotherm. The leaching potential of the sludges were then assessed by calculating the separation factor. And according to Weber and Chakravorty, a separation factor greater than 1 indicates a favorable, unfavorable process. Equal to 1 indicates a linear process. Variation between 0 and 1 indicates a favorable process. And equal to 1 indicates an irreversible process. From the graph presented here, you can see that within the range of initial phosphate concentration tested, for the 3 sludges, the separation factors varied between 0 and 1, indicating a favorable process, and by extension, indicating that the 3 sludges are appropriate phosphate adsorbents. From here, you can also see that amongst the 3 sludges that were studied, the lime iron sludge produced the lowest separation factor, implying a decreased potential to leaching, as well as indicating that it had the highest adsorption potential amongst the sludges. The effect of temperature was studied within the typical range 25 to 55 degrees Celsius as determined from the literature. These are the results for lime iron sludge, and from here you can see that an increase in temperature resulted in an increased adsorption, which implies that the process was endothermic. For lime iron sludge, there was a 35% increase in adsorption as the temperature increased from 25 to 55 degrees Celsius, and similar results were obtained for lime sludge and alum sludge. In order to quantify this effect of temperature on the adsorption process, the Langmuir constant K was used to calculate the Gibbs free energy, and a plot of the Gibbs free energy versus temperature revealed a straight line from which the enthalpy was read off as the intercept and the entropy change was read off as the slope. From this graph, you can see that within the range of initial temperatures tested, the Gibbs free energy is negative, indicating a spontaneous process. The enthalpy change is positive, which indicates that the process is endothermic, and the entropy change is also positive, indicating that there was a high affinity of the adsorbent for the adsorbate, and furthermore, it suggests that there were some structural changes between the adsorbent and the adsorbate. The table here shows a comparison of the maximum adsorption capacities obtained for several adsorbents which were reported in the literature and those used in the study. And from here, you can see that the lime iron sludge used in the study reported a maximum adsorption capacity which was higher than several of the adsorbents reported in the literature. The alum sludge and lime sludge used in the study produced adsorption capacities which were comparable to that in the literature. So following the adsorption studies, desorption or extractability of the phosphate retained on the sludge is critical regarding its recovery as a resource. Methods of desorption include anion exchange membrane, solvent extraction, acid-base extraction, and electro-ultrafiltration. And according to the literature, acid-base extraction is the most cost-effective and was therefore selected for use in this study. The desorption potential of 3 acids, 2 bases, and distilled water was studied. And the graph here shows the results for lime iron sludge. A 0.1 molar concentration of sodium hydroxide was able to extract the maximum 91% of the phosphate retained on the lime iron sludge. Similarly, for lime sludge, a 0.1 molar sodium hydroxide extracted a maximum of the retained phosphorus. In this case, it extracted 94%. For alum sludge, however, a 0.1 molar sulfuric acid or hydrochloric acid was able to extract 94% of the retained phosphate from the alum sludge. These significant extraction abilities of the acid or base indicate that chemical processes are involved. However, if you look at the 3 graphs, you will see that distilled water is able to extract some of the retained phosphorus. So it extracted 8% from the lime iron sludge, 22% from the lime sludge, and 8% from the alum sludge. This indicates that there are some physical processes involved in the adsorption process. Based on the findings of this study, the following inferences regarding the mechanisms can be made. The kinetic data was well represented by the diffusion chemisorption model. The increased adsorption with increasing agitation confirms the presence of film diffusion and it is postulated that diffusion followed by chemisorption controls the adsorption process. The equilibrium data for alum sludge was best represented by the Redlich-Peterson isotherm, while the equilibrium data for lime sludge and lime iron sludge was best represented by the Langmuir isotherm. Desorption studies verified the presence of both physical and chemical bonding, and temperature studies indicated that the process may be spontaneous and endothermic, with the adsorbent having a high affinity for the adsorbate, and suggests that there were some structural changes between the adsorbate and the adsorbent. I will now go on to talk briefly about the future work that can be done in this research. Today I presented results to you that were based on a single component study. Future work will include adsorption studies to be done in multi-component using synthetic solution as well as real wastewater, and these will look at the effect of competing ions on the adsorption process. Similarly, desorption studies will be done using multi-component solutions. Phosphate recovery studies will attempt to form a precipitate following the desorption studies, and a potential method of doing this is by deposition. An example of a phosphate that can be formed, a precipitate is aluminium phosphate. Sludge regeneration studies will attempt to determine the number of times a sample of sludge could be reused for adsorption and desorption purposes. The adsorption, desorption, and recovery data will be modeled, and statistical analysis will be done using SPSS and response surface methodology. And finally, the disposal or reuse of the spent material will be studied. So after the sludge has exhausted its useful adsorption and desorption potential, we will look at proper disposal or reuse of the sludge such that there is minimal negative impacts to the environment. One potential area of reuse is for the adsorption of heavy metals such as copper from wastewater. The outcomes of this research will provide an alternative for sludge reuse and thus eliminate the negative impacts associated with current disposal practices. It will provide an alternative for phosphate adsorption and consequently reduce eutrophication. And it will provide an alternative to recover phosphorus, which is a non-renewable resource. This brings me to the end of my presentation, and like always, it is beyond me to not acknowledge those key persons in my research. First of all, to my supervisor, Dr. Clint Sutherland, for his unwavering guidance and support throughout my research, to Professor Stout for her invaluable contribution, and to Vikesh, Donald, Riel, Sarah, Vitra, Gavin, Neil, Craig, and Shivan for their significant contributions throughout my research. Thank you all.